Continuing on physical chemistry, chapter 18, we're in section 14 now. We're going to talk about a two-particle rigid rotor. Now this too is not a realistic model, but we're looking at a piece at a time with the real model we want to look at. So we have two particles here, mass 1, mass 2. So the distance from center to center, we're going to call that lowercase r for radius. Now the potential energy is going to be equal to 0. And we're also ignoring vibrations now, since we talked about vibrations separately already. Then r, like I said, is the distance center to center. The book calls it d for a distance or diameter, I guess, I don't know. But then dV, the differential, the potential energy, remember that's minus the force times the difference in radius, but that's equal to 0 because we said this radius is constant because they're not vibrating. So the energy is just going to be the kinetic energy plus the rotational energy. It's the kinetic energy of the whole thing as a pair. We're going to ignore that for now and look at the rotational energy. And then again, we're saying the vibrational energy is equal to 0, and the potential energy is equal to 0. Continuing on physical chemistry, chapter 18, we're in section 14 now, talking about the two-particle rigid rotor. So the energy of rotation for this system is J times J plus 1 times h bar squared over 2I. Now I is the moment of inertia. Hopefully when you had physics you talked about moment of inertia already for a classical system. And then mu is reduced mass. Now this number up here, J, this is another quantum number. This could be 0 or 1 or 2 or 3, etc. So remember, when J is equal to 0, you won't have any rotational energy. So it is possible for the two-particle rigid rotor to not rotate at all. Now for a diatomic molecule, the moment of inertia is just going to be this reduced mass mu times r squared. See the diagram on the previous slide for r. If there were 3 or more, then it would be a lot more complicated, so don't worry about that. We'll just do two-particle rigid rotor. Now mu, I'll save you the math. You probably did it in physics anyway, but it simplifies to mass 1 times mass 2 divided by mass 1 plus mass 2. Now this number J here, we call that a rotational quantum number. So that's the third quantum number. Now we had N, and then, let's see, I can't even remember the other one. But anyway, we have J now, too. Continuing on physical chemistry, chapter 18, section 14, we're talking about rotation now of a two-particle system. So the rotational energy levels, just like the other forms of energy, they start at the lowest. So J can be equal to 0, and then energy is equal to 0, which means no rotation at all. And then J is equal to 1, energy is equal to 2. To simplify the units, we mean this divided by h bar squared over 2I. So you can multiply that back in if you want to know the actual energy levels. But anyway, then for J equals 2, E equals 6, and then for J equals 3, E equals 12. The important thing to remember, the formula for energy I showed you is parabolic. So these are not evenly spaced. Now, we need to talk about polar coordinates now. We got the two particles here, M1, we're going to call that the center. So M2 will be the whatever position relative to M1. The distance between them we said is r. It's center to center. I didn't show that very well here, but hopefully you remember from before. So we have our x-axis here, our y-axis here, and our z-axis here. Now if we take this particle and we project it down onto the xy plane, it's down here. This distance here is r sine theta. Now the angle from the xy plane up here, oops, well I have it backwards. Theta is actually the angle from the z-axis, how far out we are. So it'd be, what is it, 2 pi, or pi over 2 minus theta would be this angle here. But, okay, so on our xy plane, the particle projected down here, from this angle from the x-axis is called phi, or phi. Keep in mind this is backwards from how they normally do it in math classes. If you took multivariate calculus, you probably learned this was theta and this was phi. I got those switched around on purpose in quantum mechanics to do it backwards. So now that we know these angles, we can find out our xyz coordinates if we're given these angles and the radius. So x, it's the r sine theta, that's what I mentioned about the projection here, times cosine of phi. And then y is going to be r sine theta times sine of phi. And then z, that's just the r cosine of theta. Continuing physical chemistry, chapter 18, section 14, we're talking about rotation of a two-particle rigid rotor. So the wave function psi for rotational energy, obviously we're talking about quantum mechanics, is the product of two other functions. The function capital theta, which is a function of the angle theta, and the function capital phi, which is a function of the angle phi. Now, notice this formula doesn't include r, the radius, because we said radius does not change. We're talking about the rigid rotor here. Now, this capital theta function, it depends on two quantum numbers. J, which we already talked about, the rotational quantum number, and then mj, which I'll get to in a bit. And then this other function, capital phi, it depends only on this other quantum number we're about to talk about, mj. So, we talked about j already, and I showed you how to convert to polar coordinates. mj is the component of j along the z-axis, whatever. Now remember, j can start at 0 and then go 1, 2, 3, etc. It's quantized. mj, it goes from minus j to positive j by ones. So you can go from minus j plus 1, blah, 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 all the way to 0. So mj can be positive, negative, or 0, depending on what j is. Continuing on physical chemistry, chapter 18, section 14, we're talking about the two-particle rigid rotor. So we talked about mj, and another way to write that is it goes from 0, plus or minus 1, plus or minus 2, plus or minus, etc., all the way to plus or minus j. That's the same thing I said on the previous slide, but maybe you'll understand this form better. So, as an example, let's say that j is equal to 2. That means mj could be minus 2, or minus 1, or 0, or 1, or 2. So, for a given j, there are two j plus 1 values for mj. So let's go do a simpler one, j equals 1. Then mj is equal to plus 1, so we write the psi rotation is equal to psi 1, 1. Or mj can equal to 0, then we write psi rotation is equal to psi 1, 0. Or for mj is equal to negative 1, we write psi rotation is equal to psi 1 minus 1, or negative 1. So remember though that these three, they all have the same j, and we showed how the energy was found from j. Therefore, each energy level j has 2j plus 1 degeneracy. Continuing on physical chemistry, chapter 18, section 14. So let's talk about an example of a two-particle rigid rotor. Like we could have hydrogen or chlorine. Those the superscripts here indicate which isotope, because it's going to make a difference in the mass, and we need reduced mass to do this. So we're going to have two different energy levels, like j equals 0 to j equals 1. The reason we did that, we're not going to know absolute energy, but we know from a difference in energy, from the energy of the light being absorbed or given off for a light spectrum. In this case, it's going to be 4.17 times 10 to the negative 22 joules, which is in the microwave region. And of course, doing microwave spectroscopy is possible. Or let's say we have carbon 12 and sulfur 32. Then, again, we're going to go from j equals 0 to j equals 1. So there's 0 energy here, there's a certain amount of energy here. This difference in energy in this case is 3.246 times 10 to the negative 23 joules, which again we can observe in spectroscopy techniques or whatever. So, let's say we want to find the distance between the center, the nucleus of this carbon atom, to the nucleus of the sulfur atom. That's just the bond length then. So we need to apply some of the formulas we just learned. So we have energy for any level j is just j times j plus 1 times h bar squared over 2I. Remember, I is the reduced mass, or not the moment of inertia, which is the reduced mass times r squared. And of course, delta E is just E1 minus E9. So we substitute in this formula here, we're using 1, j equals 1, so 1 times 1 plus 1 times h bar squared over 2I minus 0. So that simplifies just h bar squared over 2I. So then we solve that for I, and we get h bar squared over delta E. the book has h, so we have to substitute h bar is h over 2 pi. So we get h squared over 2 pi squared times delta E. Substitute in the numbers, Planck's constant is 6.63 times 10 to the negative 34 joule seconds. That whole thing is squared. And then, of course, 2 pi squared. And then we said this energy here is the 3.246 times 10 to the negative 23 joules. And then put that in your calculator. Hopefully you'll get the moment of inertia for this molecule is 3.43 times 10 to the negative 46 joules second squared. This is Physical Chemistry, Chapter 18, Section 14. I'm continuing the example of the previous slide. We had a bond between carbon and sulfur, carbon 12, sulfur 32, I think. So now we need to find the reduced mass, which is M1 times M2 over M1 plus M2. Of course, order doesn't matter, so we put in the carbon and the sulfur here. So we have 12 grams per mole. We're dividing everything by Na because we actually want the mass of one atom, not the mass of a mole. But anyway, the Na's are going to cancel out anyway. So we get 12 times 32 divided by 12 plus, oops, this should be 32 right there. Anyway, so the answer, put it in your calculator, hopefully you'll end up with 1.45 times 10 to the negative 23rd grams. So then R squared is equal to I over mu. So we solved for I on the previous slide. We got 3.43 times 10 to the negative 46 joule second squared. And then we put in mu, notice I converted to kilograms on you, so it's 1.45 times 10 to the negative 26 kilograms, just so that the units cancel correctly. And I got 2.37 times 10 to the negative 20th meters squared. Take the square root of both sides, positive square root obviously. The radius is 1.54 times 10 to the negative 10th meters, or 1.54 angstroms. So this should be the bond length between a carbon atom and a sulfur atom. Continue on Physical Chemistry, Chapter 18. We're in Section 15 now. We're talking about approximation methods. Now remember before we were talking about multiple particles, we had to assume they were non-interacting. And that's just for mathematical simplicity. And also said that's unrealistic because in real life the particles we're talking about are electrons which have negative charge, so they all repel each other. So unfortunately particle interaction, namely the electrons, it prevents exact solutions to Schrodinger's equations. So we have to approximate it instead. Now there are two methods. One is called the variation method. Now what we're going to do, we want to estimate the ground state energy of the system. And so we're going to have this trial energy. This basically trial means guess. So it's the integral over all space, of course, of our experimental function psi star. So remember star means complex conjugate still. Times the Hamiltonian, well, of psi, or phi. This is phi now because it's not on psi yet. We're hoping it's going to be psi. And it's going to be greater than or equal to energy of the ground state. So remember this H circumflex, or H hat, this is the time-independent Hamiltonian, the energy operator. And then EGS over here, this is the true ground state energy that we're trying to find. And then this phi and phi star, these are normalized, of course. Remember what normalized means, that the definite integral from negative infinity to infinity in all directions has to be equal to 1. And then remember, these are trial wave functions. These are the angle phi, like we did before, converting to polar coordinates, or converting from polar to rectangle. Now ideally, if we manage, our approximation method works perfectly, we're going to end up with the energy of our trial function is exactly equal to the actual energy of the ground state. Continue on Physical Chemistry, Chapter 18, Section 15. We're talking about approximation methods. So if that function isn't normalized, then the first thing we need to do is normalize it. Now remember, normalize would mean, well, basically we're going to throw in an n, a constant, to normalize it. So we would say the integral of the absolute value of n times phi squared, d tau. So we can pull out the absolute value of n, so that's absolute value of n squared times the integral absolute value of phi squared d tau, and that's equal to 1. That's the normalization condition. So then we just solve for this absolute value of n squared, and we get 1 over the integral of the absolute value of phi squared d tau. So then we just put that over here. So this was our original function that's not normalized, and we put this denominator down here to normalize it. So we get the integral of phi star Hamiltonian phi d tau divided by the integral of phi star phi d tau. And that's got to be greater than or equal to the actual ground state energy that we're trying to find. Now, of course, if it was already normalized and you went through this process, then that means that phi is normalized and this whole integral down here would be equal to 1. So it would still work, you just wasted a bunch of time. Continue on Physical Chemistry, Chapter 18, Section 15. So let's say for n equals 1, remember for a particle in a box we have E equal to n squared h squared over 8ma squared, where n is the quantum number, we're going to say it's equal to 1, h is Planck's constant, m is the mass of the particle, and a was the length of the box. So this, putting in n equals 1, that simplifies to h squared over 8ma squared, and then of course 1/8 is just 0.125, so we can write that 0.125 h squared over 8ma squared. Now we're going to say that psi is actually the square root of 2 over a times sine of n pi x over a. But what we're going to do is we're going to approximate it, because we don't really have a way to calculate sine except your calculator. We're going to approximate psi of x with x is equal to x minus a. Now the first thing we have to do is make sure that it fits the boundary conditions for particle in a box. And it does. If you put in at the limit as x approaches a is equal to 0, so that's one end of the box. And likewise, the limit as x approaches 0 is equal to 0. So going to 0 at both ends of the box is one of the criteria, or is the boundary conditions for particle in the box. So now we're going to find the psi star Hamiltonian psi. So our psi, we're going to say, is x times x minus a. The Hamiltonian is minus h squared over 8 pi squared m, second derivative with respect to x, of our function x times x minus a. Now in this case, I wrote it as complex conjugate, but we're talking about real functions here, so sometimes they don't even bother to put on the star there to indicate complex conjugate, because our function is real, therefore its complex conjugate is going to be real. So a real function is its own complex conjugate. I think I mentioned that. Continue on Physical Chemistry, Chapter 18, Section 15. So now we have the integral from 0 to a, because it's a particle in the box of length a, of psi Hamiltonian psi dx. Remember, it's x because it's a one-dimensional box, and there's no star because it's real function. So that's equal to minus h squared over 4 pi squared m, because I've pulled out the constants, times the integral from 0 to a of x times x minus a dx. Distribute this out and separate them. We get minus h squared times 4 pi squared m times this entire quantity. The integral from 0 to a of x squared dx minus a times the integral from 0 to a of x dx. Evaluating these, we get minus h squared over 4 pi squared m is equal to a cubed over 3 minus a cubed 2. Simplifying that, we get minus h squared over 4 pi squared m times minus a cubed over 6. And remember, h is Planck's constant, a is the length of the box, and then m is the mass of the particle. Simplifying, obviously we get rid of the double negatives. We just get Planck's constant squared times the length of the box cubed over 24 pi squared times the mass of the particle. Now this is not normalized, so we have to use that formula I showed you before, how to normalize a function. We've got to evaluate that denominator too and divide them. So we get the integral from 0 to a of psi star dx, or psi squared. Technically it's absolute value, but it's real function, so it won't make a difference. Equals the integral from 0 to a of x squared times x minus a squared dx. We're going to multiply this out and separate them so we know how to evaluate the integral. So we get the integral from 0 to a of x to the 4th dx plus a squared times the integral from 0 to a of x squared dx minus 2a times the integral from 0 to a of x cubed dx. Plugging in, or evaluating from 0 to a, we get a to the 5th over 5 plus a to the 5th over 3 minus a to the 5th over 2. That's all simplifies just a to the 5th over 30. That's our denominator. So now we can divide this by this. Continue on physical chemistry, chapter 18, section 15. So we're continuing on approximation methods. So now we divide the numerator by the denominator so that we have a function that we need. So our e prime, this is our trial, we have the numerator here, h squared over a cubed over 24 pi squared m, and then our denominator, a to the 5th over 30. We combine that, we get 30h squared a cubed over 24 pi squared m a to the 5th. Canceling a little bit, we get 5h squared over 4 pi squared m a squared. Simplifying this, we get 0.127 h squared over m a squared. Now remember, our actual function was 0.125. So notice 0.127 is slightly larger than 0.125. Which means we were close, but not exact. So our percent error, you just take 0.127, everything else cancels out, so I left it out. 0.127 minus 0.125 over 0.125 times 100%, you get 1.6%. That sounds good, but you think about it, that's barely 2 significant figures, and sometimes you want 4 more significant figures. So 1.6% error is actually too high for the standards of quantum mechanics. So instead, what you'd want to try is a more advanced function, like maybe x squared times x minus a squared, or something like that. Something that will better approximate your sine wave. Okay, continue on physical chemistry, chapter 18, section 15. The second approximation method we're going to talk about is the perturbation method. Now the variation method is what we just did, and that is for the ground state only. And the perturbation method, that should work for the ground state or for excited states. Now, I already mentioned this before, but sometimes Schrodinger's equation, it can't be solved exactly. Remember, if you get a whole bunch of particles, and they all have negative charge, because we're talking about electrons, they all contribute to the potential energy, V. So when you have dozens and dozens of electrons, calculating the potential energy is just too darn complicated. So we're going to have 2 different functions here, well 3 actually. So this should look familiar. The Hamiltonian of psi of n is equal to energy times psi of n. So this is going to be our approximation. And then we're going to use not to say exactly. So the Hamiltonian not times of psi of n is equal to the actual energy not times psi of n. That's our exact value. So you should be able to find the difference between these two by subtracting. So you get the Hamiltonian approximation, that's going to be the actual Hamiltonian not plus this Hamiltonian prime. So we're going to say this difference is our perturbation. So this Hamiltonian prime is the perturbation. Continuing on physical chemistry, chapter 18, section 15, we're talking about the perturbation method of approximating a wave function. So we have this energy for the energy level n, the first term. So the integral from psi, now not means exact, star, Hamiltonian prime, psi, and exact, d tau. So then we say this en terms, we get en naught plus en1 plus en2, etc. So we're adding up all these correction terms. Now remember, this is like an average. The Hamiltonian, we're finding average energy. So en1, we say this is the first order correction term, which is going to be the largest correction term. And then this here, this is our second order correction, etc. And each successive one gets smaller and smaller. So it's kind of like, I think it was the virial equation of state when we were doing gases, when we had all these correction terms, and you just go out as many as you have to until you get the amount of precision that you need.